In Chapter 10, we're definitely going to change gears for sure compared to Chapter 9, and we're going to go back to a lot of the same concepts we studied throughout this course concerning derivatives and integrals and the related concepts. In this chapter, the two major concepts are parametric equations and polar equations. So there are 4 sections in Chapter 10, but this first section in Chapter 10 really isn't a calculus lesson. It's either going to serve as a review if you've seen parametric equations before this class, or maybe an introduction to the basics of parametric equations, so that in 10.2 we can talk about the calculus involved with dealing with parametric equations. So before we talk about these things called parametric equations, we need to do a quick little review of motion in one dimension. We first saw this at the end of Chapter 2, and then again at the end of Chapter 4. So given a position of a bug, just for an example, on a line, let's suppose its position is given by the function t squared minus t, where time is of course the t. X is just its position on this horizontal line, which we can consider to be the x-axis. If we wanted to find the velocity of the bug at any time, we'd of course need to take the derivative of position, and in this case that's a nice and simple task. It would be 2t minus 1. So a really quick review of what you saw at the end of Chapter 2, but that's kind of what you need as we transition into this new topic of parametric equations. So here's the question we have. Let's pretend this bug breaks away from this horizontal line and now is free to move about the xy plane. How could we describe the path of this bug if it lived in our xy coordinate axis? Well, we would need 2 pieces of information. When it was on a horizontal line, we just needed to know its position along that x-axis. And that's why we kind of usually wrote our position function as x of t. If it's moving along the xy plane, we need information not only in terms of its x direction, but also its y direction. If the bug moves around the xy plane, we must have 2 equations to describe its motion with respect to time. We'll have one in the x direction as a function of time, and we'll have another in the y direction as a function of time. These 2 equations that are both with respect to time are what we call parametric equations. If f and g are continuous functions in terms of time, then the 2 equations that we call x and y, which will have some sort of variable t in it, will be called parametric equations. And that t that's present in both x and y equations will be called the parameter. So parametric equations allow you to describe the path of something in 2 directions, or in this case in our xy plane. So let's start with 2 basic ones in a sense, and let's pretend our bug is now moving with respect to x as cosine t and with respect to y as sine of t. Of course, those 2 give us position in the x and y direction with respect to time, so we would call those 2 parametric equations. Because we have parametric equations, we can plug in values of t and plot the path of the bug. So there's really no difference between graphing parametric equations and regular equations. The only thing different here is we're picking a time, and that's what's going to give us a point x comma y. So let's go ahead and do that. I'm going to go ahead and pick time equals 0 minutes. At 0, our x position would be cosine 0 or 1. Our y position would be y of 0 or sine of 0, which is 0. So at time equals 0, the bug is at the point 1, 0. So I'm going to go ahead and plot that point right there so we can see where the bug is starting. I'm going to pick another time, and there's really no specific times I'm picking here. I want to say they're random in a sense, but if you think about this for a moment, we really don't want to pick a time of like 1 or 2 or 3 minutes because we'd have to plug that into a cosine and a sine function, and of course without a calculator that would be really difficult. So instead of picking whole numbers, let's pick some numbers that would make more sense in terms of plugging them into our trig functions. So as a second time I'm going to pick pi over 4 minutes. If I plug in pi over 4 into my x parametric equation, I'll get cosine of pi over 4 or square root of 2 over 2. If I plug in pi over 4 minutes into my y equation, I'll get sine of pi over 4 or again the square root of 2 over 2, which is telling us that the bug is at the point square root of 2 over 2, comma, square root of 2 over 2. So I'm going to plot that point again. And you can see already in these 2 points I've plotted, there's a motion to the plotting of these points. Not only are we plotting points and we're going to connect them, but we're connecting them with a certain motion as time progresses. The next time I'm going to plug in is at pi minutes. Again, don't really want to pick whole numbers, as that would be very difficult to compute those numbers. So at t equals pi minutes, or about 3.14 minutes, the x position of this bug would be cosine pi, or -1. The y position of this bug will be sine pi, or 0. Which means after pi minutes, or about 3.14 minutes, the bug will be at the point -1, 0. Just for the sake of not filling up this space with more points here, you can kind of see the path of this bug. As it turns out, this bug is moving in a circle, and it's actually moving around the unit circle, if you recall. And not only that, and this is kind of the key to parametric equations, there's a motion to the way we plotted the points. Of course, we can graph this circle, and that's not a problem. But as it turns out, we can also describe the motion, and in this sense, we can describe it as the bug is moving counterclockwise around our unit circle. Okay, so kind of transitioning from that last example to kind of really clarifying what these parametric equations are all about and the path that they take when we're dealing with our regular coordinates, our rectangular coordinates, which are just the x, y points that we're used to dealing with. Those things, or those equations or points, tell you where an object has been. So it's been at some point, but you don't know anything more about that point necessarily. Parametric equations, on the other hand, tell you when an object has been at a particular point, and it's because of that component of time. You're plugging in a time to get an x and a y value. So we can conclude then, in a sense, when an object has been at a particular point. To do this, again, we're using this third variable, t, which we're calling the parameter. So let's take a look at another set of parametric equations, and we want to sketch the curve just like the last one, described by those parametric equations, except here we want to sketch it from -2 to 3. So to do that, we can make a table of values. I'm going to pick all the whole numbers from -2 to 3. And all of those times, -2, -1, 0, 1, 2, and 3, we're going to take those and plug them into our 2 equations. To get our x component, we'll plug in those times into the x equation. To get the y component, we'll plug those times in to get the y or into the y equation to get the y component. Once we do that, we can see our little table of values here that's been pre-populated, and we can plot those points. And of course, connect those points with a smooth curve. So again, it's not only about the graph that these parametric equations trace out, it's also about the direction or the path that these points took as time went from one point to another point. And also something to mention, it is okay for time, in a sense, to be negative. These aren't necessarily always real world, so to speak, equations. So we actually can consider t not always as a time necessarily, but t can be negative. So we have our graph here, and if you notice, the points we plotted out first went from 0, -1 to -3, -0.5. So I'm going to kind of indicate some of the points that we saw here. At our starting point, which was at t equals -2, we were right here. At t equals 0, we ended up here, and at t equals 3, we ended up here. So if I wanted to indicate the direction that the graph took as time progressed, or as t got bigger, we could use arrows to kind of indicate that direction. In the past example, I kind of had the bug kind of indicating that direction, but it's just a lot easier, of course, to just draw arrows to indicate the direction of motion concerning this graph. Your calculator does these graphs for you, and it would probably be a good idea to kind of get familiar with the way your calculator can graph these for you. So, of course, I just have the animations here of the screens you would see in your TI-89, so I would certainly recommend you pause after this slide and attempt to do this just to make sure you can get this graph. The first thing you got to do is go into mode, graphing mode, and change it to parametric. And then you'll be allowed to enter your x and your y equations. T1 would be t squared minus 4, as you see up here. Your y equation, and it's got a t1 there because you can graph multiple parametric equations, so we just want to do t1 for this particular case, would be t over 2. You're not typing in x's here, you're going to have to type in t's. After that, you can change the window. You'll notice I changed the t from from negative 2 to 3 because that's the interval we're given. And then you can adjust the x and the y window accordingly so you can see enough of the graph, just like usual graphs that you've done before in this class. After that, it'll graph the picture that you see above. And on top of that, if you look at the way it graphs it, it will animate it in the direction that you see the arrows above. So it can be helpful from time to time to see that direction play out in case a problem would have a piece of it that would require that you know that. Okay, so how do we plot parametric equations? Well, as you saw in the first two slides, it could just be as simple as picking some points for t, plugging them into x and y, and creating a table. And of course, we did that in a analogy, so to speak, ever since Algebra 1. If you ever needed to graph a particular function, you picked some x's, found the y's, and plotted those points. But maybe there's a different way to approach plotting these parametric equations. Again, the first technique we can do is plug in values for t, make a table, plot those points, and we can trace it out in a sense. Another technique that is very useful in plotting these is to throw away the parameter. Or in other words, technically usually called eliminating the parameter. We can get rid of the parameter t and then write an equation in terms of the regular way we're used to seeing it with just x's and y's. So eliminating the parameter from parametric equations will give you just one equation of the form that you're usually used to, where you have y equal to some function in terms of x. So how do we do this? Well, there's two kinds of problems in terms of eliminating the parameter, and I'm going to do one of each type. So this first example will be the first type of eliminating the parameter, where we're going to solve for the parameter in one equation and plug it into the other equation. So here we want to graph the parametric equations x equals t cubed and y equals t squared. So what we're going to do is solve the first equation for t. If we do that, we'll take the cubic root of both sides, and then we'll find that t is equal to the cubic root of x. What we're going to do then is take that t, because that's what t is equal to, and plug it into the other equation. And of course we're plugging it into the y equation because we want an equation where we have y equals something in terms of x. When we plug that in, we'll get the cubic root of x all squared. Recall, to simplify that to an exponent, we would change that root to a 1/3 power. And when we have a power to a power, we'll go ahead and multiply those two, and then we're left with the equation y equals x to the 2/3. If you happen to know what that looks like, we could graph that without ever really making a table of values for our two parametric equations up here. Y equals x to the 2/3 has that shape. And kind of notice, we can bring in some of the old terminology we saw way earlier in this chapter, and specifically chapter 3. Right at 0, we have a cusp where the function makes an abrupt change in direction, which would mean the slope would be undefined, if you need that little reminder there. So of course it's a really sharp point, as the little animation shows. It would really hurt if you touched it. So cusps are really sharp, and because of that, our slope is undefined at those points. If we imagine a bug for a second moving along this graph, if you were to pretend like we made a table of values, at t equals 0, the bug would be at the origin. To the left of the origin is where the bug would start. So if we were to plug in negative times, into our two equations up here, we would end up with points to the left of the origin. If we were to plug in positive times into our two parametric equations up here, we'd end up with points to the right of the origin. And of course, because of that motion, so to speak, our bug would be moving from left to right. For the second example, we're going to look at the second type of eliminating the parameter technique. In the second technique, we're going to eliminate the parameter by substituting a part of an equation that contains the parameter. So what does that look like? Well, you'll notice we know from past lessons in this class, we can manipulate powers. If you rewrite 2t as t plus t, we can rewrite that base of e separate as e to the t times e to the t. And of course, if we combine those two, we could just go back to the original equation of e to the 2t. But the reason I don't want to do that is we know over here that e to the t is equal to x. And that's why the second technique requires that you substitute a part of an equation that contains the parameter. So once we manipulate the y equation to be e to the t times e to the t, we can take that and substitute in that value for what e to the t is equal to. E to the t is equal to x, so that would really just be 3 times x, or 3x squared. So the interesting thing is, and I don't think many of us would know this or assume this, it turns out that x equals e to the t and y equals 3e to the 2t are really just the parabola 3x squared. So we can go ahead and graph that. But there's something we need to realize, and this is kind of the trick involved with this particular technique. At t equals 0, if we wanted to take a look at what was happening at that time, if we plug in 0 for the x equation, we would get 1. If we plug in t equals 0 for the y equation, we would get 3. So we know at time equals 0, the bug is at 1, 3. So I'm going to go ahead and indicate that right on the graph. And that's usually the easiest point to kind of figure out. And the reason that we always want to plug the time equals 0 point is because, of course, to the left of t equals 0, we're dealing with negative times, and to the right of 0, we're dealing with positive times. But we're not talking about the origin, we're talking about the initial starting point for our bug here in this case. So I mentioned a second ago that this might not really be the graph we're dealing with. And it's for this one reason that we really aren't looking at this entire graph. Think about the left side of our origin for a second. All the negative x values. Would those be valid in terms of this particular scenario? Well, to answer that question, let's think about taking the limit of our x component, or our x equation, as t went to negative infinity. The limit of e to the t as t goes to negative infinity is 0. If we take the limit of our y equation as t goes to negative infinity, we'll also get 0, if you need that reminder back from chapter 5. So as it turns out, as t goes to negative infinity, we're always going to get a 0. In other words, we're never going to see the left side of this graph. If we're never going to get negative values, and that's basically what these two things are saying, if we're never going to get negative values for x or y, then we're certainly not going to see the left side of this parabola. The bug will never reach the part of the curve to the left of the origin because of our two parametric equations. So because of that, we can disregard, in a sense, the piece of that graph and only look at that part. And just to again plot the path of the bug, if you pick negative numbers and plug them into your parametric equations up above, you'll get the points that are right here. And if you plug in positive numbers for t and plug them into your parametric equations, you'll get the points to the right of t equals 0. To kind of summarize all of this, not only is it important to plot these points, but it's also important to see the path that's traced out for these parametric equations. Okay, just a couple more examples here of sketching parametric equations with this technique of eliminating the parameter. Except in these two, they're going to be a little more difficult. So let's take a look at these two examples. Here we want to sketch the curve represented by these two parametric equations by eliminating the parameter. And here I'm going to use the first technique of solving this x equation for t and then plugging that in to the y equation. So if we're going to solve for t here and it's being trapped by this square root, I think a good idea would be to square both sides. When you square x, it becomes x squared, and when you square this fraction, the top becomes squared, but 1 squared is just 1. And of course, when you square the bottom of the fraction, the square root cancels, and we're left with t plus 1. X squared is really over 1, and once you realize that, you can, in a sense, imagine that we're going to take these two here and multiply them, or cross-multiply them. But we're really not going to distribute the x squared into the t plus 1. So really what it comes down to is us switching these. I'm going to take the t plus 1 and multiply it to the other side, and at the same time take the x squared and divide it to the other side. Once we do that, it's very simple to solve for t. We can go ahead and subtract 1. And in this particular case, I'm not going to stop there. In this case, I'm going to go ahead and write this as one fraction. It'll kind of help us when we plug into our y equation up here. So I'm going to go ahead and think of this 1 as really an x squared over an x squared. And if we think of this 1 as an x squared over x squared, then really we're just taking these two fractions and subtracting them. We'll end up with 1 minus x squared over x squared. And after that, we're kind of just ready to plug that into our y equation. But there's one little note I'm going to make that's very, very important, as it'll pertain to us graphing the picture that we're trying to sketch. And that's this. This fraction right here will never be negative. If you imagine plugging in times into this fraction here, where t is bigger than -1, by the way, so we can't pick anything less than that. If you imagine picking those times and plugging them in, when you take the square root, of course you'll get a positive number, and since there's only a 1 in the top, this x equation will always be positive. So that's a very important note to make as we think about what the potential graph might look like. So if we make that little note, we're ready to go in terms of the steps of this problem. So now we can go ahead and take the t and plug it into our y equation. So we're going to definitely end up with a mess here because we have fractions within fractions. But the first thing we can do to help us here is we can take the denominator of this top fraction, because of properties of fractions, and move it to the bottom of the overall fraction. Of course, it's going to be multiplied by the entire bottom of this fraction. So that's going to look like that. We're going to move the x squared to the bottom of the overall fraction. And the reason that's not only appropriate to do, but very helpful to do, is if we multiply this x squared to this term and to this term, in the first term, we'll get the x squareds to cancel. So we'll end up with 1 minus x squared. When we multiply the x squared to the 1, we'll end up with just plus x squared. And then you'll notice things work out really nice. The x squareds in the bottom would cancel, and we're just left with 1 minus x squared. So as it turns out, these two fairly intimidating, in a sense, looking parametric equations actually simplify to the one simple equation, 1 minus x squared. So keep in mind, in terms of this graph that you see here, why we're only looking at half of this upside down parabola. Going back to this idea here, we can't have any values for x that are smaller than 0. So when we're graphing this, we only want to consider the right side of this upside down parabola. And on top of that, x cannot be equal to 0. So of course we're going to have a hole here because x cannot be equal to 0. Aside from that, I have 3 very important points plotted here. I plotted the points for these particular times. The reason I plotted these particular points is so we could see the motion of the way we would be graphing this particular graph. When we have the negative time of negative 0.75, we'd be starting off, in a sense, right here. If I plugged in time equals 0, I'd be at the point 1, 0. And if I plugged in some positive time, like time equals 3, I'd end up at that blue dot there. Ultimately, you should be noticing as we go from negative times to positive times, we're moving in that direction. And that's, again, kind of one of the components to these problems, is not only graphing these parametric equations, but seeing the way they get traced out, or the way maybe a bug or some object would move along this line. One more example involving eliminating the parameter, and this one's going to be a little bit different than the first one. This particular problem is going to require that we use a Pythagorean theorem identity. Unfortunately, with these two parametric equations, really neither of the techniques, in a sense, will work. We have to rely on a particular Pythagorean identity so that we can get this to work out. And of course, this equation here is always true. It doesn't matter if we're dealing with parametric equations or not. Sine squared plus cosine squared always equals 1. So really what we need to do is take these two equations here and square them so that we can end up with a sine squared and a cosine squared. And once we do that, we can take those and plug them into our Pythagorean theorem identity. So definitely not something you would have known to do ahead of time, but this is again another technique for getting one single equation. Okay, so let's go ahead and do that. The other thing we need to realize, and we're going to have to recall a little bit of pre-cal knowledge here, is because both of these arguments inside of our trig functions are 2 theta, we can of course change our Pythagorean theorem identity to reflect that. As long as you change both of these thetas both to 2 theta, that is a legal move concerning the manipulation of these trig identities. Okay, so now we can go ahead and do what I said a moment ago. If we move the 4 over by division here in this x equation, we'll end up with x over 4 equals sine 2 theta. We don't want sine 2 theta, we want sine squared 2 theta. So if we square both sides of this equation, we'll end up with x squared over 16 equals sine squared 2 theta. And that's great because then we can take that and replace that here. Same process goes for the y equation. We're going to divide the 2 to the other side, and since we want a cosine squared 2 theta, not a cosine 2 theta, we'll square both sides, and we'll end up with y squared over 4 equals cosine squared 2 theta. And again, this we're going to replace here because it's equal to cosine squared 2 theta. When we replace those two things, we'll end up with this conic section equation. X squared over 16 plus y squared over 4 equals 1. And here's where, for the sake of time involving this topic, since it's a review topic, I won't go too in-depth with conic sections, so certainly review your knowledge of conic sections as it's going to play a part in this chapter. But as it turns out, this conic section is an ellipse. And without again going into too many details of the ellipse, this 16 tells you something about the graph, and this 4 tells you something about the graph. This 16, if you take the square root of it, of course being 4, will tell you how long half of the major axis is. You'll notice the x is 4 units this way from the origin, and 4 units that way from the origin. So that's what that 16 is telling you once you take the square root of it. The same thing goes for the 4 in the bottom with the y. If you take the square root of 4, which is 2, you'll get the 2 units this way for the minor axis, and you'll get the 2 units this way for the minor axis. So just a very, very quick overview of conic sections involving ellipses. So again, make sure you're kind of up to speed with at least circles and ellipses in terms of the equations and how they graph. After that, we can again talk about this idea of the parametric equations and the path that an object would follow along these parametric equations. If you were to pick theta equal to 0 and plug it into the x and the y over here, we'd end up with this point 0, 2. If you were to plug in more times, negative and positive, you would notice that the path that was traced out goes in a clockwise direction. Again, you can practice all of this using the calculator or just making a table of values and seeing the path that the points would be plotted as you graph these parametric equations.